Generally, user data containing sensitive information is encrypted at the network or application layer. To meet the requirements of carriers and enterprise customers that have high requirements for network security, AES-based encryption at area interfaces can be used to improve the security of user data transmitted over microwave links. So, what is AES-based encryption? AES-based encryption at area interfaces uses the Advanced Encryption Standard, AES, to encrypt user data transmitted over microwave links. AES, which is a variant of original, is a block encryption standard adopted by the federal government of the United States. It has been widely used all over the world. Note: different keys are used to encrypt and decrypt data in the transmit and receive directions of the equipment. Although the keys are different, the working principles are the same. This document describes the working principles of AES-based encryption at area interfaces only in one direction. The following is the flowchart of AES-based encryption at area interfaces. The user configures the authentication code after enabling AES-based encryption at area interfaces. The NE periodically executes the encryption authentication process. The NE executes the key switching function when encryption authentication is successful. The key update time arrives, where a key is forcibly updated on an NE. The payloads of the microwave frames transmitted and received at both ends of the link are encrypted after the keys are switched successfully. Now, let's look at the encryption authentication process. The NE periodically triggers the encryption authentication process after AES-based encryption is enabled at a microwave port on an NE. Note: authentication request responses are transmitted through overheads in microwave frames. After AES-based encryption is enabled at the microwave port on NEA, the transmit end, NEA transmits an authentication request to NEB, the receive end. The request carries a 64-bit random number, REC-A, generated by NEA. Based on the save authentication key AK, authentication code pre-configured by your user, and the REC-A in the received authentication request, NEB uses the digital logarithm SHA-256 to calculate a message authentication code, MAC. NEB sends the REC-A and MAC back to NEA through an authentication response. After NEA confirms that the REC-A in the authentication response is generated by itself, NEA uses the digital logarithm SHA-256 to calculate a MAC based on the saved authentication key AK and REC-A. NEA then compares the calculated MAC with the MAC in the authentication response. If the MACs are the same, the authentication is successful. NEA and NEB begin to generate and switch encryption keys. If the MAC addresses are different, the authentication fails and services on the microwave link are interrupted. The next part is the key switching process. The NE initiates a key switching process when encryption authentication is successful. The key update time arrives, where a key is forcibly updated on an NE. Note: key negotiation request responses are transmitted through overheads in microwave frames. Based on Diffie-Hellman, DH, NEA generates a new DH key pair, private key XA and public key YA. NEA generates a 64-bit random number, RNA, and uses the authentication key AK and RNA to encrypt the public key YA and RNA. The AES CBC mode in the encryption algorithm is used. NEA transmits a key negotiation request to NEB. The request contains the RNA and the encrypted public key YA and RNA. NEB decrypts the ciphertext in the request and compares the decrypted RNA with the plaintext RNA. If the RNAs are the same, NEB calculates the shared key based on the decrypted public key YA and the DH key pair, private key XB and public key YB, generated by itself. In addition, NEB uses the authentication key AK and RNA to encrypt the public key YB and RNA. NEB transmits a key negotiation response to NEA. The response contains the RNA and the encrypted public key YB and RNA. NEA decrypts the ciphertext in the response and compares the decrypted RNA with the plain text RNA. If the RNAs are the same, NEA calculates the shared key based on the decrypted public key YB and the private key XA generated by itself. NEA performs key switching and then sends an associated indication signal to inform NEB. NEB also performs key switching. Key negotiation of the unidirectional microwave link is successful. The last part is about payload encryption. After successful key negotiation, the transmit and receive ends use the CTR mode in 256-bit counter mode with CBC-MAC AES-CCM to encrypt and decrypt payloads and microwave frames based on the shared key, respectively.